So in this time, we are going to start looking at wave interaction. Last time we looked at the basic wave quantities and how to do basic calculations with waves. And this time we're going to look a little bit at how waves interact with other things, whether they interact with barriers or each other. Waves encounter different things all the time. So we're going to start looking at wave interactions. Now, the first one we're going to look at is what's called a fixed end scenario or fixed end reaction. And I'm going to show you what this sort of looks like, a little simulation here. There you go. Okay, so think of it as like a rope or something like that. So think of a rope where you've sort of like made a little wiggle in the rope, and the wave's coming in, and it's like tied to the wall. Now, of course, this can't move. It's tied to the walls. This is why it's called a fixed end. And if we watch what happens to the wave when the wave comes in, it actually reflects. And this is basic wave reflection. Okay, and it comes back on the other side, which seems kind of strange. Okay. So there you go. So this is what's called a fixed end reflection. Okay, so this is called a fixed end reflection. So it's hitting something really, really rigid. And when it does this, it actually comes back on the other side. Okay, which is really kind of weird, but that's the way it is. Okay, so let's go back to the little simulation thing here. There we go. So it comes in and it actually goes back on the other side. All right, so this is like hitting something rigid. Now to actually see something like this would be actually very difficult, but I'll show you something else in a little while. Now this one's a little bit different. So what's happened now is they've color-coded the wave. So it's been color-coded as white is the incoming wave. And as it goes through and goes further, when it hits, that red part is actually the reflected component of the wave. The yellow is what you'd actually see. So you can actually see the actual red at the bottom actually cancels off some of the whites. This is what you'd actually see. So if you're actually watching this, you'd see this part here go up like this and then come down like this. And of course, when half the wave has gone through and half is, oh, so you can get it right. Oh, more step. Not quite, eh? About half in, half out, the rope is actually flat for a second there, a little split second right there, and everything cancels out, and then it comes back on the other side. Okay, so the white wave represents the wave coming in, and then the red part is the reflected part on the other side. Okay, here we go. Okay, so that's what happens in a fixed end reflection. Now, it doesn't have to be a fixed end. There's also what's called a free end. So very similar. So we also have what's called a free end reflection, and it's the exact same idea, except when it comes back, it'll do something a little bit different. So we'll go back to the simulation. So again, we get a wave coming in, and you sort of think of this like as a metal post, and it's actually like attached to like a ring, and the ring can slide up and down. And when this one happens, you can see wave actually comes back on the same side because this part is actually free to move. So as the wave comes in, it shoves this thing up, it's free to move. And as this thing shoves up, it actually acts sort of like your hand does wiggling a rope to make the wave on their side. And same thing as before, we've got the incoming white wave, and you can see that the reflected part stays on the same side. And that ring actually goes really, really high. So instead of the actual reflected wave canceling out some of this and flattening out the thing, flattening out the rope or whatever it happens to be, when it goes up, the two actually build on each other to make it go really, really high. Okay. So in a free end situation, it'll actually come back on the same side. Okay, so it's kind of neat how that works. So if it hits something rigid, it goes back on the other side. If it's a free end, something more flexible, it's on the same side. Now, to get either one of these is pretty much impossible. Almost nothing is, like there's nothing really that's either purely fixed or purely free. That's where we have what's often called discontinuity. And this is the one that's more realistic. This is, you get what's called partial reflection. Okay, some goes and some comes back, and it's way more realistic than the other two. And I'm going to try. So this discontinuity here. So we've got the wave coming in. Instead of hitting a barrier, it's going from like a lighter rope to a heavier rope. And when it gets to the boundary, you see you actually have two things going on. This is partial reflection because part of the wave reflects back, part of it transmits. So part of it came back on the other side and part of it kept going. Except since the medium is heavier, the wave got smaller and part of it goes back. So since it's hitting something that's heavier, it acts more like a fixed end, and the part that gets reflected is on the opposite side. And then as the stuff that keeps on going, it's sort of like a heavier material, so it slows down the wave, it goes slower. So this is more realistic. Okay, now I can go the other way as well, where you start in something thicker and you go to something easier to move. Okay, and once again, part of it's going to keep on going, part of it will reflect back. But since the second material is actually lighter and easier to move, it's closer to being more like a free end, and the reflection actually goes on the same side. And the part that keeps on going is bigger and faster because the material is easier to move. Okay, so this is partial reflection, partial transmission, often called discontinuity, and this is more realistic. Okay, so this is where we get the partial reflection. We should also put in there transmission. Partial reflection, partial transmission. This is the one that is definitely more realistic between the two, and it actually depends on the materials, like how much reflection, how much transmission. Is it same side, opposite side? It totally depends on the material, but usually waves will split up in different ways. Okay, now I'm going to show you something kind of cool that actually connects this. This is a nice little video I'm going to show you that actually shows this actually happening in real life. So this is actually a video that I actually took all by myself when I was in Hawaii a while ago. And this is a video taken from the balcony of where I was staying. And what we have here is an area on the shore or whatever. And you sort of see that wall actually goes further down than the grass, goes down another number of feet where the water is actually hitting it. And the water waves are actually coming through and hitting it, the wall, and actually reflecting back. Now it's kind of cool. So let's play this a little bit here. So waves are coming in, and right there you can see a thing going back. There we go. Now you might want to say, hey, look, there's a wave going back. Well, it's kind of cool because that was actually very close to being a fixed end reflection. Because when the wave actually hit the wall, it was above the water, or above the neutral water rest position, actually, technically. And then when he hit the wall, since the wall was like a fixed end, that part that's actually going back out there, that's not actually a bump going back, that's actually a trough going back. So there's actually a dip in the water at that location moving back because it hit like a fixed end. It happens again as a wave comes in and hits the wall, and then it reflects back, and it looks like there's a reflection back, and it looks like it's a bump. It's not actually a bump. It's actually a shallow trough that goes all the way down. So there's actually, again, a long dip in the water going back as the trough goes back because it's more like a fixed end. So that's really, really, really kind of neat. So nerdy cool, but it's cool. So next, we're another type of interaction we're going to look at. Instead of looking at waves when they hit barriers, what about what happens when waves actually meet other waves? So when waves meet, what happens when waves meet? Well, I'm just going to show you something a little here that will sort of show you what happens. So we've got another little animation simulation type thing over here. So we've got the medium. So here we go. Here we got two waves coming in. We've got the red one and the bluey greeny one coming in. And we are going to have them go. Now, when they actually meet each other, you'll see what happens. There we go. Okay, so as the waves actually meet each other, they actually come together to make one larger wave. Okay, and this is what's called constructive interference because they're constructing and making a larger wave. Now, they don't even have to be the same size. Even if they're not the same size, they will still come together and form one larger wave together. So they don't even have to be the same size. And this is what's called constructive interference. There's two types of interference, and this is what's called constructive interference. Okay, so when waves meet, you get what's called interference. And one type is what's called constructive interference, and this is where you get a larger amplitude. You guys remember what amplitude is, how tall the wave is, how low it is. You get a larger amplitude, and that's what I am showing you guys over here in the simulation, is you get a larger wave out of it. There we go. Okay, and of course these guys would be twice as high. There we go, that big one's twice as high. Now what if they are not on the same side? If they're not on the same side, we get the exact opposite, and the waves actually cancel each other out. So you can slow down a little bit, see they come together, and when they're right on top of each other, they actually cancel each other out and it's perfectly flat, and they keep on going. Even if they're not the same size, you still get the same type of effect, except it won't perfectly cancel out. So if the red one's 5 high and the green one's like 2 low, then this you'd end up with 3. You just have to subtract. So that's called destructive interference. Okay, so there's constructive interference when waves get bigger, and there's also destructive interference when the waves get smaller. Okay, so there's also what's called destructive interference, and you get a lower amplitude out of it. Okay, so there's constructive and there's destructive. You can get a really cool thing going on. Now, there's this very, very special case that you can get with this as well, which is kind of cool. Let's bring this back. We are going to put them, make them equal to each other, or something like that. That's fine. Okay, so what we have here, we have just one single wave. But what if we have continuous waves coming? If we have continuous waves, non-stop waves, we get something that looks like this. Okay, so you got a bunch of stuff going on here, but if you're actually watching this in real life, you would see the yellow part. And if you just watch the yellow doesn't actually appear to go anywhere because it's sort of like just bobbing up and down. And this is what's called a standing wave. Even if we put them out of or in phase with each other, it doesn't matter. You still get the same effect. You get what's called a standing wave. And this is only possible because the red and blue waves, or the red and greeny blues, whatever you want to call it, they just keep on going. They don't actually affect each other. So a very special case when you have this type of thing is called a standing wave. Okay, so a very, very special case for this type of stuff is what's called a standing wave, where if we sort of have something like this, okay, oops, made that a little bit too long, make it a little bit shorter there, make it a little bit shorter, make that a little bit shorter, okay, and what happens is this thing just appears to like bob back and forth but not actually move sideways. Okay, and that's what's called a standing wave, and this creates what's called resonance. You guys may have heard, we'll talk about resonance some more, but this actually causes what's called resonance. We'll talk about that more later on. Okay, but that's a really special case for a standing wave. Now, whether it's constructive interference or destructive interference, it makes absolutely no difference. One of the biggest, most important things about the whole thing is when those waves were going by and they were doing different things. I'm going to bring them back. Oh, there we go. It doesn't make any difference. Even if we go back to a pulse, notice that the individual waves don't change. That's very, very, very important for interference. They make an overall result, whether it's bigger, smaller, they'll do different things, but the individual waves do not lose any properties. The individual waves still stay in existence and they're unchanged. Okay, so that's really important for this type of stuff. So it doesn't matter what kind of interference you're looking at. It doesn't make any difference. The individual waves always still exist. Okay, they can combine, they can do different things, but the individual waves will always still exist and keep their properties. Okay, otherwise music wouldn't make any sense. It'll just get all muddled together. When people are talking in a room, you got more than a couple people talking. If it's just get all muddled together, it wouldn't work. You can still listen to an individual person and their individual waves, even though there's waves all over the place. Okay, so these are just some different things involving waves. So what happens when they hit barriers, they can reflect and transmit. And depending on the actual structure of what they hit, how much goes back and how much keeps going changes. But waves also interact with each other, but they always keep their individual properties even though they're interacting with each other.